Hi, today I want to talk about infinite series. So basically the question is asking whether a series is converging or not. So there are a few properties or few rules that you can apply to check whether a series is converging or not. And here I have 5 examples to demonstrate some of the technique to check for convergence. So first of all, let's take a look at this series. So it is sine squared over n to the power 3 plus n. So now we can so only for this expression we can also we notice that this expression 1 over n to the power 3 plus n must be greater or equal than our expression in the question, and this 1 over n to the power 3 is also must be greater or equal than our previous two expression. So as one of the property that for a p for power series or for p series, which is something like this, n to the power of p 1 over n to the power of p. So for this kind of series, if p is greater than 1, then this series uh, will be converging. So as a result, the greater the inequality in this one, since the series of the greater expression is converging, then the series so summation of this is also converging, as well as some summation of expression like this. So the greater one is if the greater one is converging, then the smaller one will also converge. So this is one of the property that you can rewrite the series into to look for a p series that is greater than our target expression, and then using the property that the p series is converge if the p is greater than 1, so that our target series is also greater than 1. So now let's take a look at the second examples, where we also use the same property to check for the convergence. And in this case, we also find a p series that is n to the power of one half. So that is square root over square root of n in the denominator. So in this case, since again this p series is diverge if p is less or equal than 1, so that we know that this is diverging. So whatever is greater than a diverging series should also be diverging. So as a result, this expression, so this series also diverges. So as you can see that for using this property for the first two examples, so if the greater one is converging, then the smaller one is also converging. But if the smaller one is diverging, then the greater one will also be diverging. So now let's take a look at another examples where we use a ratio test to check if a series is converging or not. So basically, the ratio test is taking the limits for n approaching infinity, and then n plus 1. So the next term divided by the previous term. So in our examples, by plugging in the expression into into this test, we can rewrite our solution all the way to 1 plus 1 over 1 over n to the power of 2000, and then 1 over n plus 1. You can pause the video and then or to also do it by yourself, and then to see if you can get the same result. So as a result, so for our final solution, and then we plug in n approach infinity, we'll get that 1 plus 0 to the power of 2000. So basically this becomes 1. And then since it's 1 over to infinity, then this terms becomes 0. So as a result, the final solution for the limits of the ratio test is actually 0. So the ratio test stated that if the limits of this expression, if this limit is less than 1, then our target series is converged. Otherwise, it will diverge. So the technique here is to apply ratio test for this. Calculate the limits and then check if it is less than 1. If it is less than 1, then the series is converging. So this is the ratio test. And we also have another example called a root test. So basically, the formula for the root test is something like this. So it's also taking the limits for n approach infinity, and then take the square root of an to the power of n. So basically, take the square root to take the root of n is basically just to the power of 1 over n. So we can just first we plug in this our expression as in an, and then we take the 1 over n into the expression. So a to the power of b just for it just a to the power of b and then to the power of c is basically a to the power of b multiplied by c, so that we can multiply 1 over n into the power. So that makes 3n to the 3 over n to the power of 3 over n. And then the same thing is n divided by n. So this term becomes 1. So that you have something like eventually when you plug in the infinity, you have something like this. However, there's if we end up with this expression, then we cannot tell whether this what's the limit of from in this way. So in this situation, we need to apply the L'Hopital rule, basically just taking the derivative of the numerator and the derivative of the denominator at the same times, and then until we can plug in an infinity to the target expression. So if we rewrite this expression, we can find out that we bring the constant to the outside the limit, so that basically we're just going to take the limit of n to the power of 3 over n. So since we since our variables is n in the and our power also includes our the variables. So in this case, we also need to apply another technique. So basically, we set y equal to n to the power of 3 divided by n, and then we take the log of n. So basically, we just bring the power to the front, and now we take the limit of for n approaching infinity for the log of y, and then we find out that the limits become 0. So since the log of y has a limit of 0, then we need to take transfer back to take the limit of y itself. So the y is basically just take the exponential to the power of to 0. So basically that's give us 1. So the limits of log y is 0, but the limits of y itself is actually 1. So that gives our solution of this limits here. So the limits of y, so basically it's n to the power of 3 divided by n. So the limits of this is 1. So that our final solution is that 1 over log of 3. So for if you so the graphical representation is a increasing function for for log of x, and since log 3 must be greater than 1, since 1 is the point where we intersect on the x-axis. So this terms must be less than 1. So again, for the root test, basically we're just taking the limits of taking the limits of this expression, and then we are going to check if our result is less than 1 or not. If the root test, the limits of this is less than 1, then the series converge. So it is similar to ratio test. So this is the formula for ratio test, and this is the formula for root test. So if the limits exist and is less than 1, then our series converge. Otherwise, the series is diverging. So again, the technique that we applied in this part is that, so basically we want the x approach infinity, but we find out that the power of the expression is also contain x. So now we take the log, and then we bring the power to the front of the log and then find the limits. And at the end we just take the limits. We take the exponential of the limits, and this will give us the limits of our original expression. So these are the two techniques we use for these examples by using root test to check convergence. So now let's take a look at the fifth examples, where we have something like log n over n squared. So in these examples, we are going to use the integral test to check for convergence. So basically, we rewrite our series in terms of x, and then take the integrals instead of the summation. So so into in and there's another issue for this integral. So now we are going to use the integral by part to calculate the integral. So basically, since the derivative of d of u multiplied by v is u dv plus v du. So now if we take the integrals, it will becomes and then rearrange the terms, we'll get the integral of u dv is equal to uv minus v, the integral of v du. So now let's rewrite our original integral. So we have a log of x in the numerator, so we set u equal to log of x, and then du is just 1 over x, it's just the derivative of log x, and then dv, now we set it as whatever is left in this integral, so basically it's 1 over x squared du. And then now we take the integral of this expression, and then v is just 1 over x. So this is not du, this should be dx here. So as we rewrite our integral to uv, so basically u multiplied by v is this part, minus integral of v du. Since there's a negative sign here at the, so this becomes plus. So this is uv minus integral of v du. So now so the integral will end up in this format. So now, since this is an improper integral, so we need to take the limits. Since one of the boundary is infinity, we need to use the limit to calculate our integral. So basically, just x approach to the infinity for the integral minus the x approach 1. So if we have like if the integral is from 3 to 5, usually we just plug in 5 in this term minus we'll plug in 3 in this expression. But however, since we have one boundary approach infinity, we need to use the limit to write that x approach infinity, and calculate the limits for this, and then minus the when x approach 1 as another limit. Since we take the difference, that will give us our solution for the integral. So now we plug in infinity, so that actually we can divide it x to for both numerator and denominator. So x divided by x just will give us 1, and then log of x So log of x over x, and as x approach infinity, so that is basically 0. And then 1 over x, it just 1 over x. So in that case, this term become 1 over x over 1. And then since x approach infinity, this will just become 0. Since yeah, this term becomes 0, so basically we just divided x to both numerator and denominator, and then this becomes log x over x plus 1 over x, and then the sum over 1, so that this terms becomes 0 as x approach infinity. And then this term itself, it just yeah, as everything go to 1, so basically this is log of 1, basically that's 0. 0 plus 1 over 1, so it's 1 over 1, so that's 1. So as a result, our final answer to the integral is that the integral of 1 approach infinity log x over x squared is equal to 1. Since the integral converges to 1, our target series is also converge. So for this integral test, we just need to test if the integral converge, then the series also converge. So here we use two techniques here. One is the integral by parts, and then the other one is that we need to deal with the improper integral, where one of the boundary becomes infinity. So, and then since the integral converges to 1, then the series also converges to 1. This is another test we use to check for convergence. So here we have 5 examples, and then we introduce some of the property for the series and the test to check the convergence. So thank you very much for watching the video, and let me know if you have any question.